Brevin, she found out last night that Nana takes her phones during Hope trip, and she actually freaked out.
Oh, you're gonna be a Matt and Sierra who
I
like
didn't know
sweat
that.
from
Okay,
both.
no, I was just saying, because I do my devotions on my phone and I also have streaks. That's the only thing.
Okay, give someone your password.
That's what I'm doing.
Yeah, I have
And
Morgan
I'm gonna
do
take
my
screenshots
streaks,
of my
and
devotions.
I have paper Bible.
I have paper Bible.
Your
but
streaks
my
are that
devotions-
important?
No,
They're not important
but
to me, but they're important to other people. And I only have like 2. So.
it's not that important,
Important
but
to you then.
it's not super important, but it's also kind of a fun thing to do. It's not important, just a fun thing to do.
Because it's like really high rated.
Like sports, they're not really important. They're a fun thing to do.
Sure.
Yep. All right. So quickly, actually, why don't I just go back all the way and quickly hit all this stuff one more time.
When does
Okay.
class start?
Polar dissolves, polar, non-polar dissolves,
We just
non-polar. We talked about this yesterday and the day before. So what? Water dissolves what?
Polar.
Polar thing.
Polar thing.
Okay. And is ionic considered a polar thing?
No. Wait, yes.
Ionic is like the most polar.
Yeah, sorry.
Yep. Okay. And then, what are a couple
Nice.
examples of your typical non-polar things?
Oil.
Oil and what else?
That's right.
Diamond.
Yeah. Now your typical thing.
Fats.
Well, that would be oil, yeah.
All the oils
Okay.
just on fat.
Or are we non-polar? Or polar?
You're mostly polar.
So eventually we would dissolve.
I'm attracted to you too!
That's
That's the only thing.
As a
That's
friend.
even
As
after
a
Like, for example, last chapter we talked about wetness.
You're just gonna get
And your hair would never get wet if water wasn't attracted to it. So your hair is polar.
Like that?
Anyways,
I was so close to
Okay.
8th grade and freshman.
the other one I was looking for.
No,
Hey,
I
alright, we're done. The other one I was looking for is hydrocarbons.
Oh,
Yeah.
oh, I got you.
Yeah.
Hydrocarbons
Now.
are with.
They might.
Non-polar.
Those are just the big ones that you you might not be able to draw like Lewis structures for. But otherwise, if they give you a formula, you could draw the Lewis structure to see if it's polar or not polar, right? Doing the symmetrical test. Okay.
Wait, okay.
Okay, we talked about soluble. If something is soluble, it dissolves in it. If it's insoluble, it does not. Solubility is the maximum amount that you can dissolve at a certain temperature and pressure. Then we talked about equilibrium being the balance of two things. Chemistry and the things in chemical processes usually involve the dynamic equilibrium, which is a moving equilibrium. Why do I say that?
Because as one thing happens, the other thing happens opposite.
Yeah, but so we don't see the effects of it, but because there's no net change, doesn't mean that there isn't things moving at a frantic level, which we will get much more into.
Wait, so
equilibrium.
both of those are going to be moving equilibrium? Or just dynamic? Okay.
Static means stationary.
Yeah, that colon is not the right color.
Oh,
It doesn't
sorry.
even matter. It's not equilibrium. Ah.
Wait, what was it?
It was a light
It wasn't
purple.
even blue.
It's like purple.
Yeah.
Yeah.
All right. I just try to like throw things up there to see if you're paying attention.
Hey.
So it's like, where's
I was
Waldo?
paying attention to the colors, but not what you were saying. She's honest. I mean,
That makes me feel great.
I was thinking about
equilibrium.
Colors are more valuable than the words that Mr. Kramer said.
I don't even know how.
I disagree. I think you're great. I was listening.
Thanks.
Yeah, you listen to him in your sleep too. So.
That's why, right?
Okay,
Okay.
colors are
Okay.
visual words.
Words are not visual words coming out of my mouth.
Visible.
Okay.
I do turn this
All right.
Hello?
So, what did we say precipitating was?
Oh, it separates back out and then settles at the bottom.
Okay, yeah. It's when you've got a solid that was dissolved in solution that comes out of solution, settles out. We call that a precipitate. Okay. A solution is saturated when?
can't get any more in there.
Okay. Well.
Like, what stops dissolving?
It can't
dissolve.
Yeah, it cannot dissolve anymore.
Unless you
Super
Unless, yeah,
saturated.
at a specific temperature, the saturation point would be the maximum you could have. If you increase the temperature, you could allow more to dissolve and then cool it down slowly and get a super saturated solution.
Wait, what do you mean cool it down?
Like let it just cool down.
Slowly.
Yeah.
No, like why do you have to do, but you can just do it.
Well, you could, but then you could never say it's super saturated. Super saturated means more dissolved than what you're supposed to at a certain temperature.
At a certain temperature.
So you would raise the temperature to get more dissolved, and then slowly cool it back down. And if you slowly cool it back down, technically you have more dissolved than what you would expect at a temperature. Okay, and actually it's pretty easy to trip out a solution when you do that. Yeah, trippy. Okay, here we go. What's rate mean?
The speed at which.
Okay, all right. So how fast something will form a solution? Okay, there are two main factors. The first one is just inherent solubility. This one you cannot change. It's simply saying that if something dissolves well in something else, it's going to increase its rate or decrease its rate depending upon just its sheer nature. Does that make sense? Okay, no matter how much we mix or do things, Marty. No matter how much we mix things, no matter how much I mix oil and water, it will not what?
Mix.
Yeah, it won't dissolve. We'll mix, but it won't dissolve. Okay? So it's just because of its nature. There's nothing we can do about it. Okay? Salt and water, salt dissolves in water really well because of its nature. However, there's some other things that we can do to help it dissolve faster. And that's what number 2 is. We can affect this. It will dissolve faster is if you can get more solute-solvent interactions or collisions.
Oh, so like heat it up.
That would be a good way. Or stir it. How often do you stir something to help it dissolve? What do you think you're doing when you do that?
You're making more
Doing what my
delicious.
mom
Yeah. No, you're. Please, in the context of this. Yeah, it is going to give you slightly more energy, but not much. The main thing when you stir it is you're allowing the solvent and the solute to come more in contact and create more collision so that you're basically helping it collide so that it can surround it and separate the solute.
Is that why you have to stir like chocolate in a double boiler so that it doesn't like go in?
Say that again?
Like when you have like a double boiler and you're
A
melting
double
chocolate.
boiler. What the heck is a double boiler?
Dude.
It's when you have steam underneath you use like a pot of water and you
Like
boil
you
it
steam
and then
it?
you put a bowl on top of it so that it's not in the water but it's just like steaming underneath it.
Oh, it's like
So
how you
that
steam
it-
vegetables?
Yeah,
and stuff?
sure.
Okay.
Is that why you mix
Make it all.
whatever's in there?
Ah.
Like so that
You got me confused. I'm like, so like, for example, if I put salt, hey, if I put salt and just dumped it in water and just let it sit at the bottom, is it probably going to dissolve?
not as fast as
I mean,
Is that not a precipitate then?
it has
it has
to
to,
dissolve in
yeah, it has to be dissolved and then come out of solution. Okay, so yes, if you put salt in the bottom of a beaker, what's the matter, Gage?
I was just saying how this is so soft.
I know, for real. It's like the soft.
But I
feel
was
it.
paying
Feel
attention
it.
because
I
that's
can
what
see rabbits right now.
Yeah.
Okay, great.
Hello?
This doesn't help this at all.
Do you edit your videos that you post though?
No.
Okay.
Look at what?
Huh?
This is
Great.
all the
I'm
videos.
gonna
are
get
great.
blackmailed by Maddie or where was I? Oh, if you just set salt at the bottom of water in a beaker or something, yeah, water will slowly take the surface salt particles and dissolve it.
Seriously?
I don't know if I would go as far as to say if you left it salt at the bottom over like 10 years, it would all just dissolve. I'm not sure about that. Because it probably creates a barrier at some point where it wouldn't dissolve. But it would make sense if water cannot even get to the lower layers of the salt, there's no way that's going to, so it would only be able to take it off the surface anyways. But if you stir it, you're making the salt go all the way through the water, coming into many, many collisions with the water particles, allowing it to break apart the solute and surround it and dissolve it. Okay? So, can I affect this at all?
No.
No, it's just the nature of it. Can we affect this?
Yes.
Yes, and that's what the next slide is. Although I think you guys figured out some of these things. Okay, we just talked about stirring. How would a change in temperature affect collisions?
Hotter, 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 hotter makes the collision
Higher energy.
Higher temp. If you increase the temperature, increasing the kinetic energy, right?
Which makes it go faster.
Which makes them move faster. If they're moving faster, they're going to collide a lot more. Okay? How about surface area? Now, when I say changing the surface area, am I referring to increasing the amount of surface area or decreasing?
Increasing.
Wait, what?
Do you want as much surface area available?
A more.
Why?
Because then there's more contact with the.
So let's say
With the salt.
I have a
huge
beaker.
tube that's like this.
2 beakers, and in one beaker, I dropped a sugar cube in there. And in another beaker, I ground up that sugar cube so that I had a bunch of just grains of sugar all the way.
I was thinking change the
So
surface area.
what would have to happen is the water molecules would never get to the inner part of the sugar cube until it removed the outer part of the sugar cube. But if you create more surface area, you have more collisions exposed that are going to allow
I
you
thought you
surface
were
area.
referring to the salt thing.
I thought so
you
too.
did
I
that.
thought you said surface area of the water. I was thinking, how in the world is
I
that?
mean, kind of. I mean, I don't know how you ball up water.
Wait, so
But
you're
so let's say you have like a little, like those things over there that have pH scales. Let's say you have salt at the bottom of that. Only a little bit of water is going to touch that salt. But
Sure, I mean, yeah. I mean, it kind of, it does go both ways. When I'm talking about this, I'm more referring to, usually you have plenty of surface area of your dissolving thing.
you're saying the one on the left is going to dissolve faster?
No.
No.
It's slower. It's,
Oh, okay. I thought that's what you're saying. That's why I
This
said
has
slower.
more surface area exposed
Yeah.
than that does.
So you
No, an increase of surface area.
how is that?
this is the
increasing?
solid.
You have way more particles
This on
per
the
unit
left.
volume.
You
The water
increase the
can't
surface
reach
area of the
inside
salt.
sugar
You
to sugar
Oh,
Not
Yeah.
oh,
This has been,
okay.
I've broken it up so
Yeah.
that all of the particles essentially could be touching water. Yep.
So more surface area is
Okay. Now this probably makes decent sense to you guys, I'm assuming. Okay? When you are trying to dissolve a liquid or a solid, you increase the temperature, it causes the solubility to go up. Kind of what we talked about due to the amount of increasing collisions. Okay? This probably will make sense if you think about it, but maybe not right off the bat. When you're trying to dissolve a gas, adding more temperature actually makes the solubility less. Any idea why?
Too far away.
What do you mean too far away?
It makes them spread out more.
Okay, sure. You could say it makes them, is that what you're kind of getting at? Makes it spread out more. It has more to do with the fact that gas particles are already really energetic, so it's very difficult to get them to stay in solution already. You give them more energy, they're probably even more likely to break away. What did you say? Too crazy. Too crazy, essentially. Does that make sense though? And they're already really highly energetic. That's why we can't get a lot of gas to dissolve in liquids anyways, right? And we have to pressurize them in order to get a lot of it to dissolve because you've got to squeeze them closer together and you got to slow them down so that they're not going crazy. Okay, but if you add, this is partly why now I know, yes, when you have pop and you undo the top, yes, you lose the pressure, but also part of the reason why it becomes, the gas escapes well is because it usually, it's going to escape better at room temperature than if you have it in, a refrigerator. So it's twofold. Yes, it doesn't have the pressure holding it in, but the temperature's increasing, and so gas is going to escape more due to that as well.
So high pressure, lower temperature is what you want for gases to dissolve.
Yep. Which is why we pressurize our pop bottles, and we don't want to drink pop more warm. That's part of it, but yeah.
I thought the higher the temperature, the more space the liquid would have to.
Okay.
That makes sense,
Yeah,
too.
it might help you to be able to separate the solvent to allow space, but you also got it's a bigger effect on the fact that gas is already moving really fast. You can have a lot of space, but if you got a particle moving around so fast, it won't even attract it. Does that make
How's
sense?
it packed?
Were you at church last night?
Package pop?
Yeah,
Yeah, we pulled up.
Whoa.
I was there till 10:30.
Okay, calm
I
down.
never saw.
Natalie was judging you for not going to church, so.
All right, judge. Okay, so if you look at this, now on that previous slide it said that solids dissolve better with an increase in temperature. It's not 100% always. Most of the time, yes, but not always. Here's a visual that shows this solid, when you increase the temperature, its solubility skyrockets. This one steadily increases. This one increases fairly well. Adding temperature doesn't help salt dissolve that much. Okay? It doesn't. Believe it or not, the reason why salt will even dissolve at all is because it's a higher probability if it's dissolved than if it were staying close together. It actually, from an energy standpoint, isn't even favorable. So, anyways, but here is one that is a solid, and you increase the temperature, it actually decreases the solubility. So there are some outliers. It isn't always in every, but for the most part, we're going to assume that increasing the temperature increases solubilities for liquids and gases. How does pressure affect? Okay, this probably makes sense. You could pressurize something as much as you want when you're trying to dissolve solids and liquids, and it will do nothing. Why do you think it will do nothing?
Just be as no flow
Oh, because they're not very compressed.
Yeah, so they're already as compressed as they can do, so compressing isn't going to cause it to dissolve anymore. It's not going to have any effect. Okay? However, it will have a substantial effect on what? Gases, and we experience this, like I said, with our pop cans and stuff like that. Not the only thing, but we also have a decent amount of atmospheric pressure that's pushing down in our lakes and our oceans, and that's partly why we get as much oxygen gas in the lakes that we have.
Wait. Why do pop cans explode when they're so cold?
Because liquid expands.
Well, there's more liquid than there is. There's
No,
more liquid in
they
ice.
explode and they're not like ice exploding.
No, but there's more
solid.
liquid in
Slushy.
pop than there is carbon dioxide.
Well, it expands, so the water
When it
in the pop
explodes, it is
will
not frozen
expand.
at all.
Okay,
Oh, I
let me
see.
explain. The water that expands causes that enough
Whoa,
pressure,
wait a minute.
and obviously the CO2 in there is still in the gas form. Does that make sense? So you get the added expansion of the solid and the pressure of the gas that will cause that to explode.
But why is it when water?
Hey, stop going on these rabbit trails.
Because
No,
usually when you freeze something, the molecules start to move slower, which is the last.
Yes, but not slow enough to get the gas to liquefy. CO2 takes a really cold temperature to
But that
liquefy.
doesn't matter though.
How cold?
Like negative 100 degrees Celsius or more. Like it's really cold. That's why if you touch dry ice, solid CO2, it will burn you real quick.
I touched it.
Yeah, like that. But I mean, if you were to hold, okay, if you were, yeah, that's like.
Can you bring in?
You want me to bring in dry ice?
We did that, Mr.
So
Benjamin.
let's
I
bring in
love.
dry ice so I can
We did that,
burn
Mr.
myself.
Kramer. These tests are so good.
Yeah, they just make the farting noise. I know.
No,
What?
just to slide it,
Oh.
because gas constantly coming out of it, so it never touches the
Yes,
surface.
you never heard dry ice on a hard
It
surface.
goes.
Kind of makes a.
Really?
Well, we did that, Mr. Finch slides
We
too,
made
because
us
it never
wear
touches
gloves
the
and we used
surface.
them when we were like
Oh,
12 years
because
old.
gas is
Because
always-
gas is always, yeah, it's like, yeah.
I don't know why they don't make
Hockey
hockey pucks or something out of that.
Yeah, because they would eventually evaporate.
Well, like, you gotta get some technology. in there.
Okay, okay. All right, almost done here. Henry's law. This is just a This is technically a gas law that we didn't specifically talk about in the gas law chapter. It says that the solubility of the gas increases as the pressure increases, and that makes sense. We said the pressure affects the gas, right? Makes it dissolve more. Yes.
I'm gonna make a puck.
All right, you do it.
That people are gonna.
How expensive is it?
It's gonna be so.
Dry ice?
small.
Not that much. I could probably get dry ice at the. You could probably go buy it. Well, you might have to be 18.
How do you make it?
Make it cool it down and pressurize it.
Dry
Do
ice
you
ball.
not make it?
You would not have the technology.
Celsius. I
Um,
know how to make a vacuum now though. Have to charge it.
Heat it up, plug it, cool it down.
Partial vacuum,
If I had a vacuum in my house, I would have so
You
much
don't have a
fun.
vacuum. You do have a vacuum at your house.
Okay,
yeah.
guys.
Alright, so here's your equation.
I love that.
Is this a direct relationship or an inverse
That's
relationship?
inverse. Direct.
The direct. As the pressure goes up of a gas, the solubility of that gas goes up, and vice versa. Okay? Now we're not going to do. We're not doing math problem today. You might see one math problem with this on your homework, but we've done how many gas law problems in the past? I think you guys will be fine.
No homework yesterday.
I think this is the last thing here.
Lesson.
Effervescence. This would be like.
Is this like why I got or pop gets black?
Yeah, like so when you take and unscrew.
That's how we unscrew.
Why is it not through a solid? Like dry ice.
That's probably got a different name. That's probably called sublimation. I don't know.
Ever sublimation.
I don't know.
Effervescence.
So effervescence is really like when you take off a pop cap, you hear that. Yeah, that's a whole bunch of air molecules.
And when you're drinking hot liquid, now you know what you're drinking. You're like, why would you?
How often do you drink pop at night?
Disclaimer.
Obviously,
Obviously, when you're hydrated.
what?
Are we done?
Can you come check my?
How much time do we have? What else are we gonna do?
How much?
I'll look.
What are you doing?
53.
Yeah, and who's worried about?
About 12 minutes.